In this video, I'd like to discuss how we can use the Laplace transform to solve initial value problems. So from a bigger picture perspective, we start off with an initial value problem where the initial values occur at t equals 0. Think maybe a spring mass problem. We can sometimes potentially solve this directly to get the solution of the initial value problem. Let's call it y of t. But it could be a time-consuming process, or it may be something that our previous chapter 4 methods do not apply to. So instead, we can take an indirect approach where we take the Laplace transform of the initial value problem using the formulas that we see above. And what this does is it gives us back an algebraic equation in terms of big Y of s. So it turns a calculus problem into an algebra problem. We solve the algebra problem, which is hopefully a manageable problem, and then the inverse Laplace transform will bring us back to the solution. And usually this inverse Laplace transform is going to be the most time-consuming part of the process. Let's go ahead and investigate an example. And a common such problem is to solve an initial value problem using the Laplace transform. So we begin by just taking the Laplace transform of the differential equation. So break it up over each term and pull out constants. And then for each of these terms, we know what that corresponding Laplace transform is. From the previous page, the Laplace transform of y double prime is s squared big Y of s, and remember big Y of s is the Laplace transform of little y, minus sy of 0 minus y prime of 0. And then we have 5 Laplace transforms of y prime. So that would be s big Y of s minus y of 0 plus 4 Laplace transforms of y equals 0. And then we go ahead and we substitute in our initial values. Y of 0 equals 1, and y prime of 0 equals 0. So I'm just going to cross that term off. And now we group our terms together. We have some number of terms that involve big Y of s. We group those together on the left. There's a big Y of s times s squared plus 5s plus 4. And I should note that we do need to be careful to distribute that 5 through to both terms. Then I'm going to move the other terms remaining to the right. The minus s is going to be a plus s on the right, and the minus 5 is going to be a plus 5 on the right. And now we isolate the big Y of s. So note that the quantity multiplied by big Y of s would factor as s plus 4, s plus 1. So that big Y of s is equal to s plus 5 over s plus 4, s plus 1. And what we are looking for is the solution of the initial value problem. And remember, the solution, little y of t, will be the inverse Laplace transform of big Y of s. And in order to find the inverse Laplace transform, as we've seen with many examples, requires a partial fraction decomposition. Instead of going through the details of the partial fraction decomposition, which is very quick and efficient in this case, I'm just going to write down the form. Here what we would end up getting is minus 1/3 over s plus 4 plus 4/3 over s plus 1. And with that in mind, the solution of our equation, both of these are going to be of the form of an exponential, so e to the at. In the first case, a is minus 4, and in the second case, a is minus 1. So we would have our solution as minus 1/3 e to the minus 4t plus 4/3 e to the minus t.